Welcome everybody to the NSERC PermafrostNet seminar. Today's seminar is by Allison Plourde. The title is Measuring Active Layer Dynamics with InSAR. Allison has been an MSc student at Simon Fraser University's SAR lab for 3 years. She completed her B.Eng in Aerospace Engineering at Carleton University, where she was first introduced to SAR remote sensing as a research assistant at the Water and Ice Research Laboratory. Her research focuses on measuring permafrost surface dynamics using advanced InSAR techniques, with a primary study area in Inuvik in the Northwest Territories. Standard InSAR methods are often limited to summer acquisitions due to the refractive effects of snow on the InSAR phase. Under the supervision of Dr. Bernard Rebus, Allison has been developing methods to measure surface dynamics and long-term subsistence trends year-round. Having spent 7 years living in the Yukon, Allison came well prepared for the challenges of working in the North. She's eager to apply her skills in remote sensing to research that feels both scientifically impactful and personally meaningful. So, after that, we're going to have a nice presentation by Allison. And if you have any questions, please put them in the chat. And at the end of the presentation, we can open it up for a Q&A. So thank you very much. And over to Allison.
Thank you, Tristan. So my thesis project has been titled Measuring Active Layer Dynamics with InSAR. And here's a lovely photo here of some of the field work that I've done. So this is just north of Inuvik along the ITH, and you can see it's in this lovely tundra rolling moraine. Here is another example of one of these in-situ sensors that I have at my sites. I have 6 in-situ stations. So each of them have a vertical deformation sensor, which is basically an inclinometer on a tilt arm and then a snow depth sensor. And so this metal pipe in the middle is drilled about 12 feet down into the permafrost. So this is serving as a stable point. And then on this lever arm, you could kind of see it here. There's a bit of a platform here. So this arm is free to move up and down with the permafrost. So I could get vertical deformation over time. At each of the sites, there's also an anchored reflector. So that's anchored down into the permafrost and serves as a stationary reference point, and a floating corner reflector. And so you can see this floating one is just on sort of a metal raft that's resting on the vegetation. So it's also free to move up and down with the active layer as it freezes and thaws. So for the InSAR component, I have 3 different stacks. The first is RadarSat-2 Ultrafind. This is a C-band sensor. It's on 24-day repeat, and the stack goes from about 2014 to 2023. And then Sentinel-1 Interferometric Wide is also C-band, but it has lower spatial resolution, but higher temporal resolution. It has a 12-day repeat pass. And so this stack goes from 2017 to 2023. And I also have TerraSAR X-band, has high temporal and high spatial resolution, but because it's X-band, it makes it a bit tricky to do this kind of analysis, which I'll talk about a bit later in this presentation. So this is the time series I have of my inclinometer measurements. So the first site was installed in 2018, and I have data going all the way up to 2023. The long-term trend in subsidence for this red curve, site 1, is about 2 centimeters per year. And then I also have a thaw tube installed at this site. And so from 2018 to summer of 2022, this thaw tube recorded 5.3 centimeters of ground subsidence. And the inclinometer reading reports about 6.1 centimeters. So these measurements are relatively in agreement with each other. And so this is just a visual of these 2 sites. This is site 1, 2018, and then 2023. You can see that the lever arm is much more inclined. So you can see how much the ground has subsided between this 5-year span. And then in the background here, you can also see the thaw tube is at this site. And so I have 6 of these sites total. Sites 4, 5, 6, they were installed in 2022. So there's only 1 year of data for these sites. So you can see the trend in the active layer dynamics where there's continuous subsidence throughout the summer. And then as freeze back occurs, there is this rapid heave. And then throughout the winter, the curve is relatively stable. And so just to give a brief overview of the fundamentals of InSAR, so what I'm looking at is the difference of phase. And so a InSAR signal has both amplitude and phase. It's an electromagnetic signal. And so what InSAR looks at is the difference of phase. So that's basically the change in the path distance from the ground. So that can be a component of deformation, which is the signal that I'm looking for, but also has all these other components that will delay or change the signal, such as atmosphere, topography, snow, other changes such as vegetation changes, and then of course sensor noise. So this is just an overview of the interferogram generation process. You start with a single look complex image. So this is where there is amplitude and phase, where the phase is an imaginary number. And then you register these to a common master scene so that all of the acquisitions are lined up with each other. So you can compare pixel to pixel. And then you do the interferogram deformation or the interferogram generation, which essentially is just the complex conjugate of two of these single look complex images. And so that's basically a multiplication of the amplitudes and a differencing of the phase. And so that differencing of the phase is that desired signal for InSAR. So on top of that, you need to do topographic corrections, which is done with a DEM. And then there's other processes such as baseline optimization and atmospheric screening and phase filtering to finally get to the final product where we can start to get the deformation signal. And so this is just a quick visual overview of sort of the techniques that are being used in this project. So you see here I have the corner reflectors. From summer to winter, this anchored corner reflector will stay the same and it'll be the reference point. And then this floating corner reflector is allowed to move up with the active layer as it expands during freeze back. These corner reflectors, they also have Lexon covers over them, and so they're independent of the snow signal. So what you could see is snow has the impact of refracting the radar signal, therefore it increases the path length. And so it's difficult to use interferograms that are taken during winter months. You need to account for this snow phase. So just a quick overview on the mathematics behind this. So phase resolution, it's limited to the wavelength of the radar. So for C-band has a wavelength about 5.5 centimeters, and then X-band has a wavelength of about 3.1 centimeters. And so what this means is that the phase difference is only discernible between plus or minus 1/2 of this wavelength. And so what happens is the phase becomes wrapped. So basically you go from minus pi to positive pi, and then everything, any deformation greater than that is going to be a integer multiple of pi. And so you need to introduce the next processing stage, which is referred to as phase unwrapping. And so for surface deformation in red here, for C-band, deformation of about 2.8 centimeters will introduce a phase wrap. So any deformation greater than that is going to require accurate phase unwrapping. And that with no depth, it's about 11 centimeters of snow accumulation. We'll start to introduce phase wraps in the InSAR signal. So I have 3 different sort of InSAR methods that I'm looking at. The first is those corner reflectors, where I'm just looking at the difference in phase between the floating corner reflector and the anchored reference reflector. Then I also use this HDS processing, which is a homogeneous distributed scattering technique. And I apply it to the summer only interferograms, so ignoring any of the interferograms where there's snow present. And so part of this is modeling seasonal displacements with the Stefan equation, which basically says that the deformation is proportional to the square root of accumulated degree days of thaw. And then finally, I have a SWE estimation technique that I'm looking at. So estimating the snow water equivalent and its effect on the interferometric phase so that I count for that and then look at the deformation signal of the SWE corrected interferograms. So here's just a quick example of the Stefan model that I'm using. And so I apply this to my corner reflector data. So the black points here are the Stefan model. And then the dark blue is the radar signal from the corner reflectors for RadarSat-2. And so the light blue sort of sandwiched in between these two dashed lines, this is the wrapped phase. So that's plus or minus, and the phase is high. And so you can see that the deformations are well outside of this wrapped signal. And so you have to unwrap the phase. And so I'm using the Stefan model here to do that with the corner reflectors. So part of the problem here is that you can see that the unwrapping is only as good as the model that you're using to unwrap it. And so moving on to the HDS analysis for snow-free scenes, this is just a 2D seasonal amplitude map. The range here is plus or minus 1 centimeter of seasonal amplitude deformation. So here I have the Sentinel and then the RadarSat-2. And if you flip back and forth between these a few times, you can see that spatially they're in agreement with each other, which is nice to see. And so this is the seasonal amplitude time series around Site 1. And you can see it's the measuring about a seasonal amplitude of about 1 centimeter. But what this is lacking is a long-term trend in the deformation. And so because there's gaps in the data, because we're not using the scenes where there's snow, the processing is losing out on that annual signal, and it's only picking up on the seasonal one. And then if you remember back to my inclinometer data, the heave and the amplitude of the heave is about like 4 to 8 centimeters. And so this is only capturing that 1 centimeter of subsidence that's happening just between about June to early September. So it's missing a great deal of the signal overall of the permafrost active layer dynamics. And so I've changed the processing a little bit here to only look at the August acquisitions going from year to year. And so in this image here, I have Site 1. You can see these white dots here. These are my corner reflectors at Site 1. And here I've plotted a time series. And so from here, you can see that the annual trend is showing about 1 centimeter to 2 centimeters a year of subsidence. And so this is, again, looking at the inclinometer data. It starts at 2018. And then from 2019, there's almost no subsidence, and then the trend continues. And so this is also reflected here in 2018, where this InSAR data is. Almost no subsidence between 2018 and 2019, and then the trend continues on. So it's nice to see when the remote sensing data corresponds to the in-situ data. So also I have Site 2 and 3 here. So at Site 2, this is a low ground. And so when I went there in 2022, this site was actually almost submerged under a bit of water. And so you could see that Site 2 here is sort of in these vertical corner reflectors here. It's in between there, and it's situated in sort of this depression on low ground. And then whereas Site 3, that's right next to it, is up on a hill. And you can see that in the spatial data of the InSAR. And then just to look at supplementary data, there's the Geological Survey of Canada thought tube dataset that was published in the O'Neill 2023 paper, where they had annual thought tube measurements from 2019 to, I should change that, it's 2018. And so I don't have any of these thought tubes. They're all sort of just out of reach of my radar footprints, with the exception of this one down in the bottom near Inuvik. But from these thought tubes, I get an average subsidence of about 6.6 centimeters per year, which is about the same as what I'm seeing for my broader spatial subsidence in my InSAR stacks. And so moving on to the SWE estimation. On the left here, I have a sensitivity map. And so the sensitivity is basically the change in phase with respect to the change in SWE. And so it varies over the topography of the scene. And so what I've done, because the SWE estimation I'm using is a topographic method, it relies on topographic variability in the terrain. So I've taken just a 2D standard deviation to derive this quality map in the middle here. And so in the yellow would be areas of higher surface topography variations and would have better predictability for the SWE estimation, whereas bluer areas are sort of more flat terrain. And so the method is not as accurate in these areas. And so just an example of what this process looks like, you start with an interferogram. This hasn't been phase unwrapped and it still has the atmospheric signal. This technique, because it works on 1 kilometer windows, it doesn't need atmospheric correction or phase unwrapping to be applied. And so what I've generated here is a SWE estimation map. It goes from 0.1 to minus 0.1 meters of SWE, and then this upper scatter plot is the SWE estimates over a stack of the winter InSAR imagery for Sentinel-1 in this yellow area, which is actually sort of the bedrock hilly area that's south of Inuvik. And you can see it agrees pretty well. I'm comparing it here with the ERA5 reanalysis data. And then this bottom scatter plot is just, again, the x-axis is the ERA5 reanalysis data. And then on the y-axis, I have various in-situ measurements. So the Inuvik and Trail Valley Environment Canada research stations, as well as my snow depth sensors at my in-situ sites. And so you can see that the spread of the in-situ data is similar to that of the InSAR data. So this is promising that the InSAR SWE estimation technique is just about as good as the point in-situ data. So looking at the sites, Sentinel-1 and RadarSat-2, these are the sensitivity quality maps on the right here. And so you can see that the sites are located in sort of this low sensitivity area where there's not a lot of topographic variation. And so the method is a little less accurate. And then the color scheme here in the scatter plots is dark green would be high coherence, so good quality InSAR images, and then the red is low coherence, where the interferogram is exceptionally noisy at that point. So it's good to see in higher coherent areas, the estimation technique is much more accurate compared to the ERA5 reanalysis data. And then finally, just as a bonus, I also have an InSAR stack over Lac de Gras in the Northwest Territories. And the great thing about this region is there's a lot of bedrock. And so when you're doing phase unwrapping, you need to have a stable reference point to unwrap all your scenes from. And that's so the issue with my RadarSat data and Sentinel data and that's north of Inuvik is there's not a lot of bedrock that is stable to unwrap my scenes to. So this area, all the pink here is bedrock regions. What's also great about this region is I can get the shape file for this surficial geology. I can actually compare the surficial geology to the InSAR results. And so this is just a look at what that looks like. On the left is the seasonal amplitude map. So the range is about plus or minus 2 centimeters. And then the box plots here show the seasonal amplitude with respect to the surficial geology. So you can see that R2 and R3 here, these are the bedrock regions and their average amplitude is about 0, which you would expect, as well as the glacial fluvial regions, they're much more closer to 0. And then, of course, all the till regions are showing greater amplitudes, especially the hummock till, which you would expect to have the greatest amplitude, as well as the organic. So of course, a project like this requires a lot of funding and a lot of support. So I just want to say thank you to the Permafrost Network as well as the Geological Survey of Canada, who's provided a lot of funding for this project, as well as MDA, who's supplied the corner reflectors in the RadarSat-2 imagery. And also, of course, a special thanks to Peter Morse, who's been very helpful in setting up all the in-situ stations and helping me look at the in-situ results and thinking about the permafrost data, since earth science isn't my original academic pursuit. So his input has been extremely valuable, as well as Brendan O'Neill, who came out and helped with the fieldwork, setting up my stations back in 2022. So thank you very much. That's all my presentation, and I'd be happy to answer any questions.
Allison, I have a question about the fund model. So could you explain in detail what the Stefan model is looking for, what they're calculating, what factors, parameters in that Stefan model?
Yeah, absolutely. I'll flip back. So I'm using the adjusted air temperature. So I basically take the air temperature from the Environment Canada station at Inuvik, and I subtract just a constant value to get that to the ground temperature, which I think I'm using about 3 degrees Celsius. And so the Stefan model, I basically take the accumulated degree days of thaw, so summing up this temperature data and then taking the square root of it. And so that is about proportional to the deformation. And then I use just a technique to identify the inflection points. So when you're moving from freezing to thawing. And so I have just sort of at the top here is just once the freeze back has reached back to the starting point of the data set, I stopped calculating the accumulated degree days of freeze. So it's always referenced to sort of that winter stable freeze back.
So it's an indirect model of frost heaving by the depth of the freezing in the soil, right? Because the fan model probably give you the idea what the thickness of the frozen layer. Is it correct?
Yeah.
Okay. So what the soil parameters in this formula present?
I'm actually, yeah, I don't have it, but I normalize this data. So it's just going from like 0 to 1. So it's just a proportionality. I'm not considering soil parameters or anything like that. It's just a very, very basic model.
Okay, thank you.
Yeah, thanks, Allison. That's a great presentation. I have 2 questions. As you may know, the Northwest Territory Geological Survey and the Center for Geomatics is actively working in the ITH corridor, and we're always interested in operationalizing monitoring programs based on remote sensing and field-based methods. 1 or 2 things that we've kind of been working with and would be great to get your input on is we're wondering what your thoughts are about are there any kind of different phase unwrapping models that might be more appropriate in settings like this? Maybe you're aware of other models. And B, I was really interested in looking at your August only results. And perhaps you could comment a little bit more. It may have been a bit too fast for me to follow. What your thoughts are about using an August-only acquisition versus, the long-term June to September, and then trying to kind of define rates of change that way. So we get to get your thoughts on that.
Yeah, so the difficulty with phase unwrapping in this area that I'm looking at is that there isn't a stable bedrock reference, but where there is bedrock south of Inuvik. So I can do that phase unwrapping with the Sentinel-1 data where that bedrock is located. And so basically from the analysis, you can, since you know where your stable point is, you can infer that throughout the rest of the interferogram. But what the RadarSat data that I've used, I actually have a borehole data from, I forget what the study is part of, but so I've found sort of just a borehole where they found porous till where there wouldn't be a lot of movement. And so I've referenced to that point for my RadarSat data, and it's working well for this. And so with the August only data, So during the summer, you're also going to have signals from vegetation growth, and there's going to be soil moisture. So I found that soil moisture is actually impacting a large amount of the signal, especially like in this blue area. This is sort of polygonal terrain, and it's also depressed. So there's a lot of water accumulation. There's a lot of vegetation growth in these areas. And so by looking at August, you can also see that the surface deformation is sort of levels out in August. So that helps from just getting the year-to-year signal. You're not having any major surface changes during that period. And then you're also, the vegetation should be about the same. The soil moisture, there should be, since we're way past the thawing of the snowmelt, the soil moisture should also have leveled out a bit more. Does that
great.
answer?
Yeah, great. Thank you.
Yeah.
Can I ask a quick little question? So obviously you've got the really good superficial geology information, and your study site is located close to the highway. So I guess that helps with access. Are there other reasons why you chose this location to study?
So this Lac de Gras area, this is sort of it's completely different data set that I was just asked to look at because we happen to have a radar sat data set from this. And so the purpose of choosing this location is that Stefan Gruber has a lot of in situ data here. And so we could sort of compare. As far as the site selection for the Inuvik area, that was predated my beginning of the project. So I started my thesis in about 2021, 2022. And so these sites were first set up in 2018. But yeah, I think access was basically the determining factor in setting up the site locations.
Thank you.
Allison, it's fantastic to see this come along as far as it has. Yeah, a bit about the history. Jason Epler was working here, and Jason scoped out a number of potential areas. And so these places along the ITH, he zeroed in on some of them just because it was so much easier to access. Yeah, still a lot of ankle twisting involved in getting some of these sites set up, that's for sure. Allison, the question that I'm wondering about is, based on the lessons that you've learned from the instrumentation that are installed and your results, if Northwest Territories or any other group was to set up a monitoring program, can you comment on just, the lessons learned, things that are worth including in a monitoring program, things that maybe would be nice to have but not required, that sort of thing? Like, was it beneficial having the frost tube versus the heaving arm versus the floating corner reflector? Like what are some of your takeaways just on that side of things?
I think the biggest thing is because like most of the data is at that site one, where there is a frost tube and there is the inclinometer, and that's the longest running data set. So it would have been helpful to actually have thaw tubes at other sites to compare to so the thaw tube and the inclinometer, they agree at site one, but the InSAR doesn't totally agree at site one. The amplitudes are much less. And so to have other thaw tubes to confirm the data at different sites would have been very helpful. Also, it's just the limited scope of the data. Like InSAR, you need about 10 years before you could really, really lock down the trends. So that's sort of the biggest limiting factor, I think, with the InSAR component of this. Does that answer the question?
Yeah, no, I just, we put those floating corner reflectors out there as kind of a, experiment. And I was just wondering if amongst the thaw tubes are things that, or frost tubes, I guess they are all thaw tubes in most places, but the frost tubes, they're a good benchmark. And I think a lot of us are considering using more and more of them, even though they have been around. They're maybe not used as much as they could be. And I just wasn't sure if this floating corner reflector thing was a good idea, if there was too much error associated with it or what. So I think you've answered that.
Yeah, with the reflectors, it's because these amplitudes are so great that it's really hard to unwrap the phase with the corner reflector data. It really relies on having a good model for that unwrapping, which is basically going back to the Stefan equation, which I like. They could be useful if there was a ground temperature sensing equipment maybe that could have been added so you could get a better model locally.
Great, thank you.
Hi, good morning. Very interesting presentation. I'm just curious, do you have like people working for you locally, like from Inuvik and on the highway? And how did you identify these areas to study?
So we don't have anybody working for us. Basically, these were done and the setup takes like a couple of days. And so it was just myself and Peter and then other people from our lab, depending on who was working at the project at the time. So we don't have anybody working for us. And so the site selection again was there's a couple sites that predate me entering the project. And so those were decided by Jason Epler, where he found that they were good potential for the InSAR data and close to the ITH, which made them accessible. And then for myself, my considerations were just, again, accessibility and getting slightly different terrain in the data set.
Interesting. Thanks.
I wonder if I can ask a question just regarding the location. Are you far enough off the highway just regarding the dust from the highway?
Yeah, they're about 200 to 400 meters off the highway, so a bit of a trek in that terrain. So I think, yeah, I think they're far enough to get away from the dust from the highway.
Okay, just confirming that because we definitely see an increase from the dust control of speeding up the thaw. I've seen the days of thaw.
Absolutely, yeah.
Yeah, and what would be really nice, and it just recently, the effects of tundra fire or any kind of fire that speeds up a lot, and we've noticed that in the last couple of years, where increased moisture being released is what looks evident anyway from some of the videos that we've seen. Anyway, I just thought I'd mention that.
No, absolutely. And there was that fire in 2023, but unfortunately, like it was just out of reach of some of my footprints. So I would have loved to look at that. But yeah, even in 2023, I remember sitting at my sites and just seeing the tundra burning away.
And maybe that's a logical follow-up question if we're thinking fire, but maybe just more specifically, what are the next steps with respect to this work? I assume you're thinking of publishing this, and also what do you think are some logical next steps going forward in terms of experimental design or broader coverage, et cetera, et cetera?
Yeah, absolutely. So I'm just nearing the end of my thesis. So next steps for me is to compile all of this into the final thesis. Where the sort of delay is right now is getting the SWE estimation. So getting a good screen to remove the snow phase so that I can look at the surface deformation throughout the year. And what's helpful with that is because during freezeback, there isn't any surface deformation. So if you had accurate SWE estimation techniques, you can go from year to year and you can get a better sense of the degradation over time because you're not relying on sort of this summer period where things are going up and down and there's vegetation and there's soil moisture, precipitation, and all of that. So the next step that I'm going to see if I can try and tackle before I'm done my thesis is to try and get that method working, or at least determine whether or not this method can be used, because maybe it's not going to be effective due to the lack of variability in the terrain. Other next steps is there's the RCM RadarSat constellation mission data that's coming up. And so I think that's bit easier to get your hands on. I'm not sure if there's any high resolution images in this area, but that could be a great next step in sort of looking at the data going forward because RadarSat 2 is sort of stopped for this region that I'm looking at.
Great, yeah, thank you.
Thanks, Tristan, and thanks very much, Allison. That was really neat. And you introduced a lot of technical information related to radar remote sensing that I'm not too familiar with. But for phase unwrapping, have you thought about looking at bridges along that stretch of the Inuvik Tuck Highway as sites that might help you with phase unwrapping? I think we can assume that they're reasonably vertically immobile, but you might be able to speak to that as far as what the characteristics are for a site for phase unwrapping.
Yeah, no, that is actually something that I was looking at, especially along the ITH there. I never went forward with that just because there's a lot of noise around the ITH, because of course you have the embankments which are moving, and so you have like sort of this one good coherent point amongst noise, and then of course there's water running under these bridges, and so that's great for decorrelation as well. And so like spatial resolution is about 3 meters by 3 meters per pixel, which is getting along the size of the bridges. So they're like maybe 1 to 2 pixels. So yeah.
Okay, thanks. That's really interesting and informative for me. Thank you.
Thank you. Yes, thank you so much, everybody, for coming, letting me share my research with you.